Hi everyone, welcome back to my video about programming with Go. This video is the last part of concurrency and it's also the last video in my lecture series about programming with Go. In this video, we will cover multiplexing and shared memory style of concurrent programming. Let's start with the motivation of multiplexing to understand why we would need multiplexing. Consider the program that counts down until the new year. This program uses the time.tick function, which returns a channel on which it sends the current time periodically. The period between two sends is uh, given as the argument of function time.tick. In this example is 1 second. So the call to function time.tick in this program will send the current time every second to the channel it returns. And that channel is assigned to variable tick. The for loop count down from 10 to 1, printing out the count and receiving from channel tick in each iteration. After the loop, it displays Happy New Year. This is how the countdown program runs. So we click run and it is show the numbers from 10 down to 1 once every second, and then it display Happy New Year. The previous countdown program works okay, but now we want to add the ability to abort the countdown when pressing enter at any time. Our solution is to start a Go routine that tries to read a single byte from the standard input, and if succeeds, sends a value on a channel named abort. This is implemented by a function create abort channel, which takes no argument and will return a channel of empty struct. This function creates a channel abort, then starts a Go routine that calls an anonymous function which reads a single byte from the standard input, that is os.stdin, and then sends a value to channel abort. Finally, it returns channel abort. Then in function main, it starts with calling function create abort channel and assigning the returned channel to variable abort. To enable abort anytime during the countdown loop, we attempt to receive from channel abort after receiving from channel tick. But this doesn't work. We cannot receive from both channels simultaneously because these two receive operations execute sequentially in the same Go routine, which is the main Go routine. For example, here we try receiving from channel tick first, then it will block the abort channel. To make it work, we need to multiplex the two operations received from tick and received from abort in the for loop, so that each iteration of the loop must wait for an event to arrive on one of the two channels, tick and abort. In general, what does multiplexing channel operations mean? Multiplexing channel operations in Go refers to the ability to simultaneously wait for and handle communication on multiple channels in the same Go routine. This includes the ability to block until one of the communication operations is ready, and if multiple operations are ready at once, then randomly select one of them to execute. For example, a Go routine may receive from two channels and send to another channel. Multiplexing channel operations allows the Go routine to wait for those three communication operations simultaneously until one of them is ready and select one of the ready operations to execute. Multiplexing channel operations is done by the select statement, which lets a Go routine wait on multiple communication operations. Recall that a communication operation is a send or receive operation on some channel. Like a switch statement, a select statement has a number of cases and an optional default case. Each case specifies a communication and an associated block of statements. A select statement blocks until one of its cases is ready to run. Then it executes that case. If multiple cases are ready at once, the select statement chooses one at random to execute. The default case in a select statement is run if no other case is ready. So we should use a default case to try a send or receive on a channel without blocking if the channel is not ready. Here is the first example of multiplexing with the select statement. This is a correct version of the countdown program with ability to abort. It modifies the previous version of the countdown program with abort by using a select statement instead of sequentially receiving from channel tick and channel abort in the for loop. The select statement has two cases. The first case is receive from channel tick and does nothing when this case is ready. The second case is receiving from channel abort, and when this case is ready, it prints out aborted and terminates the program. This select statement in the for loop causes its iteration of the loop to wait up to 1 second for an abort because it waits for receiving from tick and receiving from abort simultaneously. When this program runs, it may display some countdown numbers 10, 9, 8 in the first three iterations. And during the fourth iteration, the user presses enter before the 1 second has passed. So it receives from abort before receiving from tick. Then the case of receiving from abort executes, printing out aborted and terminating the program. Here is the second example of multiplexing with the select statement. In the first example, there was only one Go routine. In this example, there are two Go routines. The program in this example has a function Fibonacci that takes two channels C and Q as arguments and calculates the sequence of Fibonacci numbers. It sends the Fibonacci numbers to channel argument C until it receives a value from channel Q. To implement this, it has a select statement inside the infinite for loop. The select statement has two cases. The first case is received from channel Q. And when this case is ready, it prints out quit and returns. The second case is send value x to channel C, where x is the current Fibonacci number. And when this case is ready, it will calculate the next two Fibonacci numbers and store them in variable x and y. The code here ensures that variable y always stores the Fibonacci number after the one stored in variable x. In the main function, we create two channels CH and quit that will be passed to function Fibonacci as arguments C and Q, respectively. The main function also stores a new unnamed Go routine, which runs the anonymous function. This anonymous function receives and displays 10 values from channel CH through a for loop and sends value 0 to channel quit. And finally, function main calls function Fibonacci, passing channels CH and quit as actual arguments. So function Fibonacci is executed in the main Go routine, while the anonymous function is executed in the new Go routine. The for loop in the Fibonacci function would run forever, sending the Fibonacci numbers to channel CH, which are then received and printed out by the new Go routine. When the new Go routine receives enough 10 Fibonacci numbers, it sends 0 to channel quit, which is then received by the main Go routine, causing it to print out quit and then return. The first two examples of multiplexing with select involve unbuffered channels. Here is another example of multiplexing which involves buffered channels. In this example, channel CH is a buffered channel with capacity 1. Through the select statement inside the for loop, channel CH is alternately empty and full, so only one case can proceed. Either send value I to CH when variable I is even, or receive from CH when the value of I is odd, where I is the counting variable of the loop that counts from 0 to 9. So this is the output that shows the alternate send and receives on the channel CH. What if CH has side 2? Does it still alternate between send and receive like this output? You can try it for yourself and see that it can output 2 sends or 2 receives in a row. Now let's see another example of multiplexing with the select statement that has a default case. In general, we can use a default case to try a send or receive without blocking. In this example, the program creates only one channel abort and it starts a new Go routine that runs the anonymous function. The anonymous function simply reads a single byte from the standard input and then sends a value to channel abort. The main function has a select statement that has one case, which is receive from abort, and has a default case that does nothing. In the case of receive from abort, it prints out aborted and terminates the program. With the default case, this program will access right away because the default case in a select is run if no other case is ready. So when you have not pressed any key, then this case is not ready, so it just automatically execute the default case and access the program. Without the default case, this program will wait until you press a key before it accesses, because in that case, it will wait until the case of receive from abort to be ready. Here is another example with the default in the select statement. This example is based on the example on the tour of Go at this link. This program calls function time.tick, which returns a channel tick on which it sends the current time every 100 milliseconds. Then it calls function time.after, which waits for the duration of 500 milliseconds to elapse and then sends the current time, but only once, on the returned channel. The channel returned by the function time.after is a variable boom. The select statement in the for loop has two cases. The first case is receive from tick and will display tick. The second case is receive from boom and will display boom and then return. So a tick is a 100 millisecond marker and a boom is the 500 millisecond marker. The select statement also has the default case in which it displays a dot and calls function time.sleep. Function time.sleep pauses the current Go routine for at least the given duration, which is 50 milliseconds in this example. The default case here allows the main Go routine to try to receive from tick and boom, but avoid blocking when those channels are not ready. So it will display the dot every at every 50 million second marker when the tick and boom channels are not ready. Here is the program with default selection on the tour of Go, which is the same one that I've shown, but also displays the elapsed time for more readability. I'm copying it to the Go playground and run it there to see the entire output. Okay, so here's the output. As you can see in the output of this program, at 0 millisecond and 50 millisecond, neither tick nor boom channel was ready, and the dot is displayed, which means the default case was executed. Then at 100 milliseconds, the tick channel was ready and executed. But a dot was also executed at 100 milliseconds. This was because there was a fraction of millisecond gap between the 100 millisecond elapsed time for the tick and 100 millisecond elapsed time for sleep. And finally, at 500 millisecond, the boom channel became ready and executed, terminating the program. Note that here you may see both the tick and boom are displayed at the 500 millisecond marker. But that's because of a fraction of millisecond gap between the 500 millisecond for tick and 500 millisecond for boom. Now let's switch gear to the shared memory style of concurrent programming. Recall that in the shared memory style of concurrent programming, the concurrent activities communicate with each other via shared objects or variables in the memory. This style is more efficient than the message passing style for concurrent activities with large data sharing, but it also has disadvantages and challenges. One challenge of shared memory is the synchronization issue. When multiple Go routines try to write to the same memory location simultaneously, the final result can be unpredictable, and sometimes it can cause a fatal error. Go's solution to the synchronization issue is mutual exclusion, which is a mechanism used to ensure that only one Go routine can access a shared variable at a time. Mutual exclusion is provided in the standard package sync with the sync.Mutex struct and its two methods, lock and unlock. The lock method acquires the token, which is called a lock, and the unlock method releases the token. Here is an example of how to use mutual exclusion. In this example, we want to make sure that the variable v is concurrently safe, meaning it can be safely shared among Go routines. Variable v is a map from a string to int, which we can use to count the occurrence of strings. In order to make v concurrently safe, we define variable mu as an instance of sync.Mutex that goes along with the variable v. To make sure the two variables go together, we put them in the same struct named safe_counter. The mutex mu guards the shared variable v. By convention, the variables guarded by a mutex are declared immediately after the declaration of the mutex itself. If you deviate from this convention, be sure to document it. We can define a block of code to be executed in mutual exclusion by surrounding it with a call to lock and unlock. For example, in the inc method of safe_counter, we want the increment of c.v at key to be executed in mutual exclusion so that only one Go routine can access the map c.v at a time. So we place the increment code between a call to lock and a call to unlock on the mutex variable that guards variable v. The region of code between lock and unlock in which a Go routine is free to read and modify the shared variables is called a critical section. So the code that increases value of a map v at the given key in the inc method is a critical section. We can also use the for to ensure the mutex will be unlocked as in the value method of a save counter. Thus, the return statement in the method value is in a critical section. Each time a go routine accesses the map v, it must call the mutex locked method to acquire an exclusive lock. If some other go routine has acquired the lock, this operation will block until the other go routine calls unlock and the lock becomes available again. After defining the save counter structure and its methods with mutual exclusion, we write the main function to test it. The main function creates a save counter C and then creates 1,000 new go routines that share the map c.v concurrently. Each new go routine calls method c.int with argument some key, so they all try to write to the variable c.v as some key. Without using mutual exclusion in the int method, this could lead to a fatal error or unpredictable result. But with the mutual exclusion, only one routine can access the variable c.v as some key at a time. As another example, we modify the concurrent web crawler version 3 to make sure no URL is fetched twice. Recall that a web crawler program simply calls a function crawl, passing as arguments a starting URL, a maximal depth of exploring, and a fetcher. To fetch a URL, we call function fetch of a fetcher with the URL as argument. This function returns the body of the page at the given URL along with the list of URLs that the page links to. It also returns an error object. Function crawl calls function fetcher.fetch to fetch the starting URL and then recursively calls itself to explore each URL that the page at the starting URL links to. The recursive part is shown in the next slide. To make sure no URL is fetched twice, we use a map to keep track of fetched URLs. So we declare variable fetched as a map from string to bool. When the starting URL is fetched by function crawl, we set the value of the map fetched at that URL to be true. So this is to indicate that the given URL has been fetched. In the recursive part of function crawl, before exploring a URL in the given list of URLs, we have to check if the URL has been fetched and only proceed with exploring if the URL is not fetched. Exploring a URL recursively requires sending an event on the channel CH, and the outer go routine needs to receive all those events in order to wait for all inner go routines to complete. Since not all URLs in the list URLs may be explored. We cannot use a for loop that ranges over the slash URLs to receive all events from a channel CH as in version 3 of the concurrent web crawler. Instead, we use variable count to count the number of events sent on a channel CH correctly. We declare and initialize variable count to 0 before the for loop that creates go routines. Then every time it creates a go routine to crawl recursively, we increase count by 1. The question is, does variable count need to be guarded? The answer is no, because variable count is not shared by multiple go routines. However, this version of concurrent web crawler may still have errors because the map variable fetched is shared by several go routines and thus is accessed in an unsafe way. We need to modify this version to guard the shared variable fetched. I leave this as an exercise for you. So that's the end of this video, and that's also the end of my lecture series about programming with Go. Thank you for watching, and I hope that you find my videos helpful and enjoy programming with Golang.